Good luck on that.
Good morning, everyone. Can I just check that the people online can hear and that we've got the sound? I don't know how we know if they can hear.
Yeah, we can.
Oh, brilliant. God, you must be shouting very loud. Don't know where you are. Anyway, excellent. Fantastic. Right. Well, welcome everyone to our BRC seminar series. Really great to see everyone here. And don't forget, there will be lunch and refreshments provided at the end. I have a few housekeeping announcements, just stating the obvious. If there's a fire, run out the back door. Nearest toilets are just to the right. Hopefully you've all enjoyed the fantastic tea and coffee that you've been provided beforehand. And afterwards there is pizza, I've been promised. So there you go. So there's a few just really important things about the BRC, I think, to highlight before we get going. And this is something that we remind everyone about each time we meet, but it's really critically important for the success of the BRC going forwards. And that's acknowledging the support that the BRC gives you. And that's not just if you're receiving a grant or a studentship. In fact, the infrastructure that's been set up as part of the BRC is really supporting many of us here in the work that we do. And so acknowledging this is really important. So there's a couple of sort of statements, just to remind everyone, again, I won't read those out. You can see them here, and there's a kind of really detailed support portal that you can log into to get all those pieces that are useful to mention. There's a reminder of a deadline coming up. So this is for the small project grants. So these are really small pots of money, up to about £25,000, which are to fund pilot projects, proof of principle work, de-risking studies. And the idea is that this will then kind of lead to future work that can come in and draw in additional external funding. So these span our different research themes, both the themes that are kind of there in place as part of the current BRC, but also some of the new themes that are being developed around psychiatry and mental health and surgery and respiratory medicine. So please do reach out to the theme leads, reach out to Sally, reach out to other people involved in the BRC if that's something you're interested in. The deadline is coming up, so you haven't got a huge amount of time. The deadline is 5 p.m. On Sunday, the 9th of March. And the eligibility is down here. It's really that, the lead applicant must be employed at the university or one of the partner NHS trusts, hold a contract of employment for the full duration of the award, and be a member of the BRC. And that really essentially means that your research aligns to one or more of the kind of key themes of the BRC. And just a reminder, if you're not actually officially a member of a BRC, just make sure you sign up, because you'll kind of get all the newsletters and information about things that are going on. Right, so today we have a really exciting set of speakers that kind of cross several of our themes. So first off, Chris is going to be talking about his research that's aligned to the respiratory theme that's being developed. And Anne Corbett's going to talk, and she's obviously a key member of the neurodegeneration theme. And at the end, you'll hear from one of our BRC students, Suhel Ahmed, who's aligned to the diabetes theme. However, there's one very important thing I need to do before we move on. So many of you know Sophie, and Sophie, I don't want to embarrass you, but stand up. It is your last day here. So, for those that don't know Sophie, I think Sophie has been probably, for me, as a sort of someone working in the BRC who just is very disorganized and can't arrange anything, has been just incredible, actually, at really managing, particularly around the sort of studentships and all that type of thing, organizing interviews. I really think personally a lot of what we've been able to do in our theme wouldn't have happened without your help, Sophie. And I know everyone speaks really highly of kind of how you've really driven that aspect of the BRC in your time here. I'm very jealous of Sophie because she's going off traveling. Where are you going to? Indonesia. So really, we shouldn't really be talking to Sophie because. But anyway, Sophie, some flowers and a card from all your friends at the BRC. Okay, so and you can all hear about Sophie's plans over pizza at the end. So first up is Chris. So I think I've got all the speakers' talks lined up. Again, Sophie has really well arranged that. So I have no idea how we're going to cope when Sophie goes. So the idea is that the speakers have approximately 20 minutes, and we'll have follow up with some questions. I think Suhel's just talking for 5 minutes at the end. So we have the two main talks for 20 minutes plus 5 minutes for questions. I will keep them as strictly to time as possible so that we don't overrun, because we only have the room booking for an hour. So Chris, do you want to come up? I don't think Chris needs much introduction, really. He's a kind of key researcher in the BRC, obviously a member of CBS, and you're going to hear about his work now. So thank you, John.
Many moons ago, I remember being at Sophie's interview panel, and we clearly made a really good choice for an interview. So this really is a sad day in that respect. So thank you for all your hard work. Okay, so I'm Chris. I'm going to talk to you about lung stuff. I've got to click at my click. That's me. There we go. So the title I gave for this was Aging and Inflammation in Fibrotic Lung Disease. That's what I'm going to talk about. I'm actually not going to mention inflammation at all. I'm just going to focus on the aging in the interest of time. And just to throw up that this was supposed to be given by Professor Michael Gibbons today. He's my partner in crime and team interstitial lung disease. That's also the lovely rainbow at St Luke's. Michael is a BRC Senior Investigator Fellow who's going to talk to you about one of the clinical trials that we've got ongoing. I'm going to end up talking about another one that we're trying to get going, so he can fill in about that at a later date. And just to throw this in straight away, that's the wider RILD team across the university and the hospital. We're a lovely, happy bunch. Good bit of photoshopping going on there to get everybody in the same room, but nice to see some of them in the room. So, what's fibrotic lung disease? Well, for orientation, those are lungs. I've cut out the brain, which is up here, and I've cut out the pancreas, which is down there. The lungs are the important bit in between those two things. And they're really complicated. You've got something like 1,500 miles of airway, 600 miles of capillary. They're always moving, because hopefully you're breathing. But that also means they're exposed to the external environment, which is fairly unique as well. So there's lots of toxic stuff that you get exposed to, whether it's oxygen, which is really evil, cigarettes, viruses, pigeons, or down in the southwest particularly, we get things like farmer's lung, where they're exposed to stuff in straw. I used to live in London, and you get the smog up there and workplace dust exposures. So there's lots of things that you're breathing in all the time, which is very, very bad for you. And on the back of that, you can see you've got genetic predisposition as well. But aging is really important. So you probably all appreciate this kind of graph showing the upward trend in the age distribution in the UK. So we are an aging population. Although Exeter kind of bucks that trend a little bit. So if you look at the same graph for Exeter, it looks a bit more like a Christmas tree. And that's because of all the students. So thank you, students, who make us all young. And why do we care about aging? So in the context of what we're doing at the moment, one of the key things we're thinking about is telomeres. Now, telomeres, you may recall, are these protective caps at the ends of your chromosomes. They're a bit like the plastic bit on the end of a shoelace. They stop your chromosomes from degrading. But there is a telomere replication problem. They get shorter as you get older. So as aging progresses, the telomeres get eroded, and eventually telomeres reach a point which becomes problematic for normal cell behaviour. So the cell will either die or they undergo senescence, which is a really key feature of aging. So we were very interested in telomeres. But what's that got to do with pulmonary fibrosis? This is the main thing that we work on. You probably haven't heard of it, but it's a pretty nasty disease. It's essentially the end stage of a whole bunch of around 200 different interstitial lung diseases. And if you group all that together, there's at least 70,000, probably more. It's quite hard to work out the epidemiology. 70-odd thousand patients in the UK that have it. The incidence is going up. Don't really understand that. There aren't any cures, and the median survival is abysmal. And what we're really appreciating more and more is how many of these also have a familial history. So there's a really interesting genetic link to all this. And if you look at those genetic links, an awful lot of them relate to telomere biology. And just so you know, if you look down the microscope at the lung, that's what the lung should look like. You've got some blood vessels in there, but most of it is empty space. You've just got this very fine lace-like pattern of the alveolar structure. And what happens in fibrosis is that gets replaced by scar tissue. So it's the same magnification. You can see all of the airspace is obliterated by matrix deposition. So all of this is scar formation. And weirdly enough, you can't breathe through that. So this is a disease where you slowly suffocate to death. And again, just to put that in context, in thinking about the sort of mortality, I'm too morbid about this, but those are the mortality figures, a little bit old now, for cancer in the UK. And that's where IPF comes in. So, as I said, you've probably never heard of it, but it has a higher mortality rate than all of these well-known cancers. And again, if you like pictures, that's what normal lung looks like when you chop it out of somebody. It's fairly sort of homogeneous. That's what IPF lung looks like. So all of this paler tissue that you can see, that's all the scar tissue that's formed. And we also have these really distended airways where they've been dragged apart because the lung becomes really stiffened. So it's not very nice. So what about telomeres then? So what I'm going to talk to you about today primarily is the work of Anna Duckworth, who did her second PhD in my group. She already had a PhD in physics and thought it'd be fun to do another one. But Anna was fantastic. She did a whole load of work on telomere biology in this condition. It's been really, really interesting. And telomeres are horribly complicated things. Please don't ask me about the biology. It is making our brains hurt. So the important thing to remember is telomeres are definitely shorter in lung fibrosis. But that's not just in lung fibrosis. They're also shorter in other diseases as well. And this is some work showing that they're also short in COPD, which is a much more well-known lung disease. So we've got shorter leukocyte telomere lengths, you might hear me refer to it as LTL, in IPF. And if you look across cohorts and stratify by telomere length, if you've got longer telomeres, that's the purple line, your survival is better. If you've got shorter telomeres, it looks like your survival is worse. So there's definitely a sort of suggestion of telomere erosion being a problem. So what Anna did fairly early in her PhD was leverage all of the data from UK Biobank to do some really complicated genetic stuff called Mendelian randomization. I should point out at this point, I'm a cell biologist, so please don't ask me how this works. But essentially, my vague understanding is it's like a clinical trial using genetics. So if you've got some single nucleotide polymorphisms that really nicely associate with telomere length and tell you about telomere length, you can also look at how well they associate with IPF. And it allows you to get around all these problems of all the sort of confounding factors like smoking and pollution exposure and so on, to work out whether or not the telomere length really does do something that drives IPF. And we compared that with COPD. And essentially, these graphs, all you need to take home from it is that it's got a slopey line. That's really important. So the slopey line tells you that there is a causal inference between telomere length, so getting shorter telomeres, and the risk of developing PF. And if you compare that with COPD, those lines are flat as a pancake. So for COPD, even though it also has shorter telomeres, there was no evidence at all of causal inference. So it really gave us sort of good data that telomere erosion was causal in pulmonary fibrosis. And we replicated that in another clinical cohort with colleagues across the UK. And you can see there's a really strong odds ratio. If you combine them down here, you get a meta-analysis of an odds ratio of about 5.8 in favour of developing pulmonary fibrosis if your telomeres get shorter. So that was the starting point. Question is there anything you can do about that? So the telomeres are getting shorter. Okay, fine. Pulmonary fibrosis is a disease of ageing. Okay. What else happens as you get older? Now, one of the things that Anna picked out from the UK Biobank data started to be some indications that things like menopause, testosterone levels, and all that sort of stuff seem to link in with the lung biology as well. So in men, your testosterone level theoretically dwindles over time as you get older. In women, you obviously go through menopause, and then certain hormones like estrogen kind of fall off a cliff, and you have a real deficit in sex hormones later on in life. So that being the case in ageing, Anna started to have a look whether there were any associations. And I'm not going to go through it all. You can go have a look at the medRxiv paper, which you'll see, hopefully get this published soon. But essentially, Anna found some really strong associations between shortened telomeres, depleted sex hormone levels, and the development of pulmonary fibrosis. So that gave us some thinking. Can we do something about that? But all of this is in UK Biobank, and we really wanted to do a local study to confirm whether or not this was the case and whether it is something we might be able to intervene with. So that's where we came up with the Starship study. The acronym just kind of fell out, and I was super happy with how this worked out. So the study of telomeres and the role of sex hormones in IPF, Starship. Essentially, with the help of the with the CRF here, fantastically helpful, we were able to recruit 102 patients, and then because of the Exeter 10,000 cohort, we were able to get, and this is crucial, age and sex matched controls to compare against. And that age and sex matching is obviously just absolutely vital for a study like this where you're looking at aging and sex. So there we go. So we had the Starship study, looked at all these things, leukocyte telomere length, blood counts, pulmonary function tests, all that sort of stuff in this cohort locally. And thankfully, we found that in the cases, the patients with pulmonary fibrosis, we saw a significant decrease in leukocyte telomere length. So that's what we would expect. So this is over and above the impact of aging. We've got much shorter telomeres on balance in the pulmonary fibrosis patients. So that was comforting. But interestingly, we also saw the decrease in sex hormone levels as well. So if you look on the left-hand side of all of these graphs, you can see the patients, whether it's the females on the left or the males on the right, they have lower sex hormone levels than their age and sex matched counterparts. And that could be free androgen index, which is a measure of testosterone, estrogen, which was unmeasurable in quite a few of the patients, and then free testosterone and bioavailable testosterone in men. Now, one thing I've learned from our conversations with the endocrinologists here is that sex hormone biology is horribly complicated. It's not as simple as measuring a sex hormone in the blood. You've got to take into account whether or not it's bioavailable or not, whether it's bound up to albumin or sex hormone blinding globulin. You have to factor in all of these things, so it's really quite complicated. But the important thing is the bioavailable testosterone, and that is definitely way lower. Okay, thank you. There we go. Right, so just to delve into that, one of those graphs a little bit more, this is from the male patients. You can see, just looking at this measure of free testosterone, for example, see the controls over here have a mean level of 0.27. Over here, the patients have a mean of 0.21, and that's actually lower than the 0.225 nanomole per litre, which is generally considered hypotestosteronemia. So if you had other symptoms of sex hormone deficit, such as low libido, erectile dysfunction, otherwise, potentially the people below this threshold would be eligible for supplementation with testosterone anyway. But you can see, as a percentage, an awful lot more of the patients than the controls are essentially deficient in testosterone. So that was quite interesting. And again, rather satisfying, discovering that the sex hormone levels also correlated with pulmonary function testing. So if the sex hormones are going to be important in the disease biology, you'd kind of assume they're going to have some sort of effect on the lung function. And that's certainly the case. So despite the relatively small numbers of females in the study, because it's a male preponderant disease, we did see a significant association with forced vital capacity, which is our sort of go-to measure for lung function in this condition. And we saw the same thing in men as well, a significant association with forced vital capacity. But because of the larger numbers, we're also able to demonstrate a significant association with DLCO, which is another important pulmonary function test that we run. So really giving us confidence that the hormone levels are linking in with the lung biology, and we've already got the ideas about the telomere length. So what are we going to do about that? Another great acronym. So we've come up with the study TRIUMPH. So essentially this is testosterone replacement in male patients with pulmonary fibrosis. So this is an NIHR bid that's gone in. The idea is to do a pretty large multi-centre study. It would end up being about 35 to 40 UK sites. It's being led by Exeter. And essentially this is testosterone replacement in males with hypotestosteronemia. We will find out in a month or so whether or not it gets through stage 1, so keep everything crossed, please. If it does, we'll try and put the stage 2 bid in and see where we go with that. But we are really, really keen to try and explore whether or not testosterone supplementation could have a beneficial impact in this patient cohort. The idea is to look at forced vital capacity as an endpoint measure. So we want to try and improve their lung function, because at the end of the day, that's what we're trying to do, is fix their lungs. But we will be looking at their telomere length and some of that biology as well. So fingers crossed. And just because this is a BRC seminar, also flag, watch this space for this guy as well. So this is Andrew Kindesky, who's a BRC PhD student who's just started in January. being supervised by all of us with our collaborators in genetics, so Gareth and Anna, already getting some great data from the start of his PhD. It's really quite depressing how quickly genetics can create good data, speaking as a cell biologist. So yeah, really excited to see what Andrew's going to dredge up in terms of further understanding of these genetic links between telomere length, sex hormones and pulmonary fibrosis. But he's already found some interesting associations that are relevant for shorter telomere lengths, so that's very, very nice. And I'll stop there. I think we're probably at time. So that's just to thank, I think, everybody who's been involved in all of this work. Anyone who's ever put together a clinical trial knows that you end up having about 47 million collaborators. So all of these people are fundamental. I'll stop there and hand over or answer questions.
Brilliant. Perfect timing, Chris. Thank you. Do we have any burning questions from the audience? There's one up there.
Do you have any evidence?
You wait for the mic then.
Do you have any evidence that people with low level of testosterone gone being more predisposed to IPF?
Yeah, so the medRxiv paper that I referred to, that essentially shows all of those associations. So the lower sex hormone levels predisposed to the development of pulmonary fibrosis. So that's all the UK Biobank data.
I have a question, Chris. So the telomere lengths you've measured in leukocytes.
Yes.
There is some evidence, I think, that different cell types might lengthen or shorten their telomeres at different rates. Certainly the basal levels, I think, can be different across cell types. So has anyone looked in actual kind of disease lung tissue at that, and how well is that correlated with the blood?
Yeah, it's a really, really important question. So measuring telomeres is kind of tricky, partly because you've got so many of them. So if you think about an individual cell, you've got 23 pairs of chromosomes. That means you've got an awful lot of telomeres. And would you believe that telomere length is different across different chromosomes and tends to be fairly predictably different across different chromosomes? So the length measurement we use, for example, measures chromosome 17, which tends to have the shortest telomeres of all the chromosomes. But you're absolutely right, it varies across tissues. So if you look in the lung tissue itself, you actually see more likely shorter telomeres than you see in blood. So actually, if you get a signal in blood, you can absolutely 100% guarantee that in the lung tissue itself, the telomere length is going to be short. And even if you don't see it in blood, generally speaking, if you look in the lung tissue, you would see short telomeres. The problem is sampling lung tissue. That's not a straightforward thing to do.
Ellie?
There's one online as well.
Oh, okay. Should we do the online one? We'll do Ellie, then the online.
Yeah, perfect. Thank you.
Hi, I was just wondering, with pulmonary fibrosis, is it reversible? So with your testosterone treatment, are you looking for an improvement or just a slowing down in progression?
So in an ideal world, I'd love to say we could reverse it. In reality, I think that's a long way off. Lung tissue just isn't very reversible. So really what we'd be hoping for is a stop to the progression. So this is, it's an inexorable disease. It's always going to progress. If we can stabilize it and maintain a level of lung function that leads to good quality of life, that would be the starting point.
Thank you. Right, okay, we've got a question online that says, any indication when in life the onset of phenotypes begins to manifest? Is it in childhood, puberty, or is it all later and driven by exposures?
It could pretty much be any of those. So you do see pulmonary fibrosis rarely in children, generally with strong genetic predisposition, but in theory it can pop up at any time. What you generally see is that it's a disease of older age, but certainly with the familial forms of the disease, that age gets younger with each subsequent generation. So I didn't show the data today, but it's quite interesting how much younger it can be with each subsequent generation when there's a genetic cause. So yeah, pretty much anywhere across the life course, but generally once you're sort of post 60ish.
Got time for one more question. There we go. Thanks.
Mine's my EDI question. Your study, was it looking in men with low testosterone level, and could you replace estrogen as well? Have you looked at that, or was it because was it a more male predominant disease from your graph, and therefore you started with men as the first population?
Yeah, that's the basic thing. So it's a male preponderant disease, which is partly what sort of points towards a role for hormone biology in the first place. So something like 70% male preponderant. The idea to start with males and testosterone supplementation, dare I say, simplicity. So HRT, certainly from the UK Biobank data, there's strong indications that could be beneficial as well. But it's a bit more of a complicated thing to build into a trial from the get-go. So we thought, let's start with what should be slightly easier to get going with testosterone. If we start seeing interesting signals in that, then what we want to do is open it up and consider HRT in women as well. I probably should have said, I mean, we're thinking that the testosterone is working through aromatization to estrogen anyway. So all of this is estrogenic response, we think.
Thanks, Chris. That's fantastic. So next up is Anne Corbett. So Anne is, I think it's right, Professor of Dementia Research, is that the official title, in HCS. Also runs the PROTECT cohort, which I imagine is going to be the focus.
Well, it might be name dropped.
Might be name dropped in the presentation. Over to you, Anne.
Thanks, John. Hi, everyone. Just make sure I'm pressing the right buttons.
Oh, that doesn't work.
That works, and that works. Brilliant. Hi, thanks, Chris. That was fascinating. Just to compliment you on your acronym choices. I think it's impossible to get a project funded unless you've got a good acronym. So it's like 80% of the way there if you've got Starship in your title. There's a bit of a theme here as well. We've got a lot of acronyms, but I'll try to make sure they're clear to you. So I'm here to talk about the vital, there's one, project, which is part of my overall PROTECT portfolio, and which is funded by the BRC. So just a reminder to those who already know, or to introduce PROTECT to those who don't. PROTECT stands for this. It starts off strong, it tails off in the acronym. Apologies for that, but it's a good name. PROTECT is my research portfolio. So it's not just one study, it's a portfolio of study around cognitive health, brain health in aging. It is a digital platform for research. So we run our PROTECT aging cohort. We also run many other studies nested on our digital platform, anything from observational studies, questionnaires, through to clinical trials and biomarker studies, which we'll talk about today. So, but just to quickly introduce the cohort to you, because our vital project is very much nested in the cohort. So PROTECT is an aging online cohort of adults over 40. We've got about 30,000 active participants now. It's been running for just over 10 years. We're in 10-year follow-up. It is entirely remote. It's completely online. So people register, consent online, and every year they come back to us. They do a really intensive assessment protocol of computerized cognitive assessment that gives us a really clear picture of how their brains are working. And they also tell us a lot of self-report data around their health, their lifestyle, their behavior, and they do at-home saliva samples for genetics. So in a really non-creepy way, we know a lot about these people, and they're really valuable to us. We've published a lot about them, but we've also been able to run studies with these people because, really critically, we have consent for recontact for this cohort, and they are very engaged and they really like doing other research, which is great because we're allowed to then deliver new research through the platform, using the cohort, using the data that we have. So PROTECT supports all sorts of additional activities on top of just being a cohort. So we have a lot of data for health research that we provide to others and use ourselves. We're able to target recruitment really specifically. So we were able to recruit, whether it's to our studies or third-party studies, by pre-screening the cohort for cognitive phenotypes, for risk factors, for genetics, etc., for location, whatever it might be. We can deliver studies, as I said, on the platform itself, so we can consent to new studies, we can run interventions online, we can follow up online with a bespoke schedule, which is really valuable. And we do this remote biofluid sampling with saliva and increasingly with blood for various different biomarkers. So, so really exciting portfolio, and it's enabled us to deliver some really cool new research. And the one I wanted to talk about today is the VITAL project, which I mentioned. And this is all about whether we can sample biomarkers for cognitive health remotely. So just to kind of give a little bit of rationale here before I get into the project, hopefully everyone's sort of aware that early detection of neurodegenerative diseases like Alzheimer's disease and other dementias is a critical priority for patients. Obviously, we want earlier diagnosis, we want people to get the treatment or even risk reduction or preventative treatment that they need earlier, and to support clinicians in achieving that. It's also critical for research because a lot of the new treatments in pipeline and drug development need to find people in these earlier stages of neurodegeneration, because that's where the treatments are likely to be most effective. So that's why PROTECT becomes very valuable, because we're able to find these people before we see actual symptoms in the clinic. And similarly for industry, now there's a growing interest in Alzheimer's disease treatments with new disease-modifying treatments in the pipeline. We're seeing the commercial sector kind of wake up a little bit to this sector and actually start to invest a bit more, and being able to identify people for their trials is hugely beneficial for them and for patients as well. But the problem is that at the moment, traditional diagnosis relies on very costly methods, usually in-person cognitive assessments that aren't necessarily hugely sensitive, quite intensive biomarker assessments like spinal fluid sampling, which is obviously quite challenging for many patients and can't be done at scale, and similarly neuroimaging. Now, this is the gold standard for a diagnosis, but there's not really anything in clinical practice at the moment that comes before that. So you sort of have a lot of people waiting in the community or possibly in primary care who are a little bit concerned, who are seeing early changes, but they're a long way from getting that intensive diagnostic assessment. And is there something we could do further down, earlier in the pipeline, so we could catch those people at the right time, figure out their risk, look at their progression, so that we get the right people through to that diagnostic endpoint at the right time in their journey? We'd be better able to triage people in that earlier risk group. We'd definitely improve the trials pipeline because we'd know who we wanted much earlier. And we'd be able to support patients better because we'd know who's at higher risk, who needs better support now, and monitor them in the community. So, and I think biomarkers has a potentially really valuable role to play here, but there's nothing in clinical practice that really does this at the moment. So there's been a lot of focus on blood biomarkers for neurodegeneration in the last few years, decade or so, because blood is easier to get from someone than spinal fluid, and it's a lot easier to take blood from someone than put them in a brain scanner. So there are three sort of main biomarkers that have come through the evidence base as the strongest. One being phosphorylated tau, which is specific to Alzheimer's disease and shows really high correlative accuracy with other AD pathologies like amyloid, etc. The second two are slightly more general biomarkers, so it's GFAP and neurofilament light. And these are markers for neuronal damage, axonal injury, that increase in neurodegeneration. And all three of these are very dynamic biomarkers, so they respond to change. So they're really useful markers of cognitive health, of treatment response and progression through a pathway. So obviously very valuable characteristics of a potential biomarker. And we've shown that we can detect these in at-risk groups. I say we, that's not my area of expertise, but colleagues and across the global sort of evidence research field have done so. And we've now, I say we again, I haven't, someone else has done this really nice sort of modelling exercise whereby these blood biomarkers can be used to actually predict risk of probability of amyloid positivity on PET scans. So that's really important because it links your endpoint, your clinical endpoint of a brain scan, which is the closest we can get to being definite about someone having Alzheimer's disease, short of taking their brain out and having a look, which obviously we can't do. And what's really nice, we now have this model that actually predicts with really good accuracy the probability of that positivity from blood biomarkers. So there's a lot of as accelerating momentum with these blood biomarkers, because they really do appear to be very indicative of risk and of progression and trajectory of cognitive health. But they're not yet widely in use. And we still have this issue of this sort of funnel, this very challenging funnel in the NHS of we can only see a certain number of people in a clinic at any one time. And could we do something at home? Could we do something before people even come in to a clinic to help to improve that funnel and make sure we're seeing the right people at the right time? And this is where the PROTECT study is really valuable, because we have this big community cohort who are really engaged. We know a lot about them. We know what their cognitive trajectory is, and they're very willing to do things for us. And this is where the VITAL study was born. So again, you can try and pick out VITAL from that long string of words, which gave us a nice acronym. And this is the study that was funded by the BRC a year or so ago. And it has three main objectives. One is, can we use tiny finger prick amounts of blood as a means of detecting the same biomarkers that we know we can detect with a traditional blood draw? So there are many, many companies out there who have started creating these, they're called microfluid blood sampling kits. Many of us might have done them during the COVID pandemic to do antibody testing for ONS studies, etc. They've become more and more widely used in studies like Zoe as well. So could we use this at-home finger prick technology to pick up those biomarkers in the way that we can with a blood draw? The second question was, if we do that, if we measure those biomarkers in finger prick blood, do they correlate with changes in brain health and function over time? And the third was a qualitative question. Will people accept this? Will people do this? Is this a reasonable thing to ask of people to do at home? So this study is still running, so I don't have results for all of it, but we've answered the first objective and we're sort of halfway through the second two. So this was a design for the first part. So does the finger prick blood give us the same measurements as a blood draw? So we happen to have a trial running here at Exeter with some PROTECT participants. So we brought them in, we took their blood, we supervised them in doing a finger prick blood kit. We've actually used two. This one here is a Capitana one, which has a very clear sort of tiny capillary that sucks the blood in and deposits it in this card. And then this one here was more of a free kind of, it was a little bit messier. Lots of blood and kind of drop it on and hope that it fills up the channel. But we supervised them in doing this in the lab, and then they took these home with them, did them themselves and sent them back in, and looked at correlations of all three of those biomarkers, tau, GFAP and NFL, using these kits. So these are the results from the first channel kit, the Capitana one it's called, for GFAP and for NFL. So you can see the sort of correlations between the two. So the GFAP, the correlations came out really nicely. I mean, we're basically seeing the same measurements using the finger prick samples as with the traditional blood draw. And the repeatability was really good as well. So we're really pleased with the GFAP one. Neurofilament light wasn't so strong for this, and we're going to keep an eye on this one. We want to continue measuring it, but we saw a much weaker correlation on that one. We're not sure why. I should just mention that all this analysis work and processing was done by our collaborators at Gothenburg. So Nick Ashton and Henrik Zetterberg's lab are totally in charge of this. So any questions about that methodology, I'll have to defer to them. But so this is what we saw. But we did see good repeatability on the NFL. So all is not lost on that one. So we're going to continue to collect this and analyse it, because actually we take the same blood for one as for both of them. So we're going to keep going on it. But it wasn't quite so strong. And then the p-tau was lovely. Phosphorylated tau, really nice correlation, really good repeatability. So this has given us a lot of confidence in this kit in particular, but also in the methodology. Interestingly, when we used a slightly messier card type that didn't have that sort of really directed blood channel, we really didn't see such a good relationship. Now, why that is, we don't know. I know the team in Gothenburg are continuing to explore this with other cohorts, but we didn't see such good repeatability. and the correlation wasn't so strong. So we have made the decision to stick with the other type because it seemed better, and to go forward to the next phase using those. This data was all published and well presented at CTAD, the CTAD conference at the end of last year, and I know they're preparing a publication which we're involved in as we speak. So then we moved on to the next phase of the study, which was much bigger. So because this doesn't require us to see people, we can go for a larger cohort. So we're looking at recruiting 500 people from PROTECT. And we've got two groups. We've got some healthy controls who aren't showing any cognitive decline and don't have any significant risk factors for Alzheimer's disease or dementia. And we have 250 who are fulfilling criteria for mild cognitive impairment. So this is based on FDA published criteria, which is standard deviations away from normal on cognitive tests. And we also look for people who had a family history of dementia. So people you'd expect to be more likely to be progressing down the pathway of potential Alzheimer's disease. We consented them to our nested study, the VITAL study on PROTECT. And we've got kind of dispensing warehouse at St Luke's now, where we send out these sample cards to them and get them to send us back. And then we send those over to Gothenburg for analysis. We then access our cognitive data and our functional data for the last 3 years plus from PROTECT, because some of these people will have been with us for 10 years, some for 3. But we've made sure we've recruited people with at least 3 years of data. And then we've also asked people how they found using the kits. You know, were they acceptable? Were they difficult? Were they painful, etc.? Would they do it at home? Which was the really critical question we wanted to ask. Is this something you would be willing to do as part of your kind of healthy aging? So unfortunately, I don't have the kind of ta-da reveal because I don't have the data yet. But where we are with this is we've recruited everyone. We've fully sampled actually over 350 now, and those have been processed at Gothenburg. So we're now in the final bit, and we've got all the data here ready. So the next stage is to match those two together and look at the correlations between cognitive trajectory, cognitive function, and the biomarker profile. So hopefully I'll be able to present this again in a few months, or we're hoping we can publish it or get it out in time for the AAIC, the Alzheimer's Association conference in the summer. So fingers crossed. So we've just got that last stage to go. But what I did want to mention is some of the feedback we've got from people, because there's no point doing all this if people aren't going to be willing to do this type of test at home. Unfortunately, at least these guys in PROTECT are very willing. So we asked them, how likely would you be to do this at home? And nobody said they were unlikely, and nobody said they're not very likely. So we kind of got maybe, quite, and very likely. So that's encouraging, and just a selection of qualitative responses that you can see. I won't read them out there, but generally people seem willing to do this. It seems to be worth the kind of short-term discomfort of a finger prick test to get information about their health and their potential risk. So really promising. Oh, can I go back? Yes, I can. So nearly the final slide, just to mention where we are now going with this work, because of course the purpose of these small project grants is to leverage further larger scale research from other funders. So really off the back of what we've been doing on VITAL, we've recently had our, get ready for some more acronyms, our REBEL project funded by the RFPB. So that is doing broadly the same thing, but we're going to do a longitudinal time series of biomarkers. And really critically, we're going to now look at how we feed that data into primary care so that GPs can interpret it, use it to inform clinical decision making. So some qualitative and piloting work in that project, which we're really excited about. And we wouldn't have got funded without VITAL, I don't think. We have our I4I programme, which is the NIHR's kind of end pipeline commercialisation piece of their funding programme. This is a 5-year programme, and the VITAL project has been really instrumental in helping us to design the protocol for this, because reactive is a big community-based cognitive monitoring concept that we've got blood biomarkers sitting behind, as well as the validation elements, and we've been able to use the outcomes of VITAL to design that protocol in the best possible way. And then we have 2 programmes, quite big ones, quite intimidating ones, shortlisted at the moment that I'm writing now. So we've got a programme grant called Darwin, which is going to take our PROTECT concept of cognitive monitoring and engagement and supercharge it with some AI modelling, and then take it out and into the NHS. So we're going to feed our data and our patients into the NHS assessment pipeline, primary and secondary care. And part of that is biofluid sampling and biomarkers and how we integrate them into the diagnostic pathway. So again, really nice legacy from Vital. And finally, this one doesn't have an acronym yet, so who knows if it'll get funded. We've got an ADDF, which is a US funder, big program around an adaptive trial, which will use blood biomarker sampling as one of the secondary outcome measures. So really nice, hopefully, legacy from the project funding from the BRC. So just finally, this is my lovely PROTECT team based at St Luke's. They've all been part of this because our developers created the platform, the Nesta study for Vital, etc. Everyone's been part of it, but the main leads have been Freya Bateman, who's one of our coordinators, who's actually project managed Vital, and Millie, who's one of the BRC research fellows, has been really supportive in a lot of the analysis and the lab protocols. I think that's it. Didn't go too far over, did I?
You were bang on.
Oh.
Very good. So we've got time for a couple of questions. I guess I had a quick one. I was just thinking about that. With the controls that you're running, what happens? Do you feed back the results? Like if someone has a high level of tau, for instance?
Not yet. Not yet. We're sort of in that pre-feedback phase, I think, whereby we haven't quite got to the point where we have enough evidence to make it a meaningful feedback. That's what Rebel will do.
Yeah.
That will take I think we need that longitudinal perspective, and once we've got that, we'll start exploring how best to feed that back. We're starting to do it with cognitive data now, which will be a very interesting exercise, because I think you can't give that information to someone and then not have something there to support them with the interpretation of it. So yeah, we're not quite there.
Okay, right. Do we have some questions? So I'll have to think of another one. What, I mean, another just practical thing, like what do these cost? Like what is the cost of one of those?
They're coming down. Well, the actual kit.
Yeah.
They're about, well, the whole kit plus processing is about $48. But they are, because of economies of scale, starting to drop, unfortunately.
I see how. Yeah.
Hi, thanks. Great talk. I just wondering, with some of the markers like neurofilament light, it's not that specific for Alzheimer's disease. So, I mean, could you be screening for other neurodegenerative disorders as well? I mean, is that something you're going to factor in?
It's certainly possible, and I know there are other groups doing that. I mean, we're currently focusing on Alzheimer's, but I suspect if Tim McDonald was here, he might have something to say about that, because you're right, it's very general. And I think what's important is when we're looking at dementia risk, we therefore need to combine these biomarkers with, say, cognitive data or other biomarkers to be sure what we're seeing is a decline in a dementia lens. And that is precisely what Rebel will do. Can we combine them to make sure we're predicting the right condition?
Hi, that was a great talk. I had a question about the diversity of your cohort, especially with regards to like socioeconomic status. How diverse is it?
Yeah, I mean, I'm not going to say it's representative of the UK, because we know that is so challenging to do. That's our goal with PROTECT, and we've got a really big sort of drive at the moment to do a lot of targeted recruitment to try to drive up some of the lesser represented groups in PROTECT. We first recruited PROTECT as a result of me running around doing a mad day of publicity, which included the Today programme. As a result, we have a lot of white, highly educated women in their 60s. Who are very engaged in research and are very valuable, and we have a really good spread in terms of location. We actually have a remarkably good spread in terms of socioeconomic status as well, because we've run deprivation scores on the cohort. What we don't have is a good spread on ethnicity, and so that's our focus now, is trying to improve that.
I just wondered if you plan to combine it with the genetics, because that would seem an obvious way of changing the prior probability. which is always what's crucial when you're looking at your positive predictive value.
Yeah, thank you. Absolutely. So as part of the reactive programme, we will do that as an exploratory secondary measure for predictive value. And then if we get Darwin funded, then that will combine those. I think we need AI coming in at some point because we've got so much data modelling that it becomes quite mind-blowing. But yes, that's where we're going. I think genetic plus blood plus cognitive plus health risk factors is probably the combination that's going to be the most meaningful.
Excellent. Well, thank you very much, Anne.
Pleasure.
We need to move on to the final talk. So, final talk of the day is by one of our PhD students, Suhel, who is going to be talking about specific de novo ACTB variants in syndromic neonatal diabetes.
Thank you. So hi everyone, today I'll be talking about one of the projects I've been working on at the very start of my PhD. So just for a bit of background, neonatal diabetes is a monogenic form of diabetes, which is typically diagnosed within the first 6 months of life and has an incidence of around 1 in 100,000 live births. It's a clinically heterogeneous condition, so you have transient forms where it sort of remits sort of weeks or months after the initial diagnosis, but does usually recur later in life. And then you have permanent forms which require lifelong insulin treatment. And then you have syndromic forms where, in addition to the diabetes, you have other clinical features. So as well as being clinically heterogeneous, it is genetically heterogeneous. And to date, there have been more than 40 causative genes identified. So in Exeter, we get samples from all around the world for genetic testing for neonatal diabetes. And in the vast majority of them, they do get a genetic diagnosis. But in around 10% of them, they do remain genetically unsolved, and this provides a good cohort for us to look into to identify the novel genetic causes of neonatal diabetes. So our aim was to use tissue analysis to identify novel causes of neonatal diabetes. So just a sort of brief overview of what we did. We whole genome sequenced 39 probands and performed tissue analysis, and then we looked for variants which were present in the proband but not in the parents, so de novo variants. And then we looked across our cohort to see if any genes were shared between different patients, and then we followed this up. So doing that, we did identify 2 patients showing a single de novo variant, and both of these patients were born with very low birth weights, diagnosed with diabetes very early in life, and also had a range of additional features. So this variant was a de novo variant in the ACB gene, and this gene is encodes for a ubiquitously expressed protein known as beta-actin, which has important functions both in the nucleus as well as in the cytoplasm. So when looking specifically at this missense variant, it has actually been reported before in the literature in at least 7 other cases. And when looking at the sort of clinical features across all of these patients that have been reported, see there are some common features, and what does stand out is that either neonatal diabetes or hypoglycemia has actually been reported in 3 other cases. And when looking at sort of missense ACB variants, they usually result in this very rare developmental disorder known as Briggs-Winter syndrome, which is very clinically variable. So even those with the same variant can have quite different features. So we looked at individuals with other ACB pathogenic variants to see if they had any reports of diabetes, but we did not see any reports of neonatal diabetes or hypoglycemia in these patients. So some statistical analysis, and this suggests that it's significantly enriched in this specific variant that we've seen in our 2 patients. So this was sort of suggested a mutation-specific mechanism leading to neonatal diabetes, and that is a sort of novel cause of neonatal diabetes. And just to sort of conclude, we are finally able to provide a genetic diagnosis to both of these patients more than 10 years after they were first referred for genetic testing. We'd recommend that the ACB gene is sort of added to routine genetic testing for neonatal diabetes, but further studies are required to understand how this variant has effects on the function of beta cells, which sort of results in neonatal diabetes. wanted to thank everyone that sort of helped and contributed to the research, and as well as the Exeter BRC for funding my PhD. Thank you.
Thank you very much for a really clear presentation. We've got time for probably one quick question or a couple of quick questions. I've got one actually, and that's obviously, I wonder if there's what were the phenotypes associated with common variation in that gene? Do you know if there's any GWAS variants? Are they linked to other metabolic traits?
It's a good question. I haven't really looked into the common, but from the rare variants, it's very variable. So yeah, features of everything.
And I couldn't help but notice the sort of neurological symptoms there. Just wondering, what specifically they were.
Yeah, so mostly it's like developmental delay. Yeah, global developmental delay. I think that's what most common across a lot of the pathogenic variants in this gene.
Thank you very much for a really clear overview of where you're at in your PhD. So I think that's it for today. I'd like to thank all three speakers for really kind of clear overview of some really exciting work that's taking place within the BRC. Please join us for refreshments and pizza outside. And again, to say thank you to Sophie for all her hard work with organising us in these types of events. So if everyone could just give all the speakers a final round of applause. There you go, that's it, last one. But you can always be